Sorry about this, folks. It does this occasionally. I'm not sure why. That'll do for now. My goodness. Teams. Lecture chat. Blammo. Okay. Sorry for the delay, folks. Cool. How is everybody doing today? I hope you guys are doing alright. I hope you guys are looking forward to reading week, which we will be having. I don't know, is the end of this class the official start of reading week for you guys? I am curious. Please, leave your comments in the chat on Teams. So, when last we spoke, we were talking about pointers. Pointers are one of the more difficult things to wrap your noodle around in C, so we're going to spend a fair amount of time talking about them and the various ways to do them. However, we were sort of off on a quick little 5-slide tangent, because if you take a look at what you get when you ask C to show you a pointer, is you get this really long string of characters, and some of you guys have not done base systems. So we're going to talk. We were talking about base systems. We were talking about the definition of binary, octal, decimal, and hexadecimal. Hexadecimal is definitely the one that you'll probably see the most of, but it's also good to be able to think in binary. If you are thinking like a computer, you are thinking in binary. So, that's all good. I was just we were going to talk about literal prefixes, which is the manner that you tell the computer how a particular integer literal has been encoded. But first, I have a couple of things. You have a test tonight? Oh, that's gross. That's gross. Good luck on the test. But that's gross. Yuck. Sorry, guys. Sorry about your test. It's terrible. So, anyway. When we are writing a program, we need to tell the computer if our numbers are in hexadecimal, or if they are in other base notations. So here are our 4 bases: binary, octal, decimal, and hexadecimal. in order for a number to be a binary number, in order to literally write a binary number, you prefix that number with 0 and then upper or lowercase b. An example would be B0, 1, etc., etc., etc. You have some long string of 1s and 0s prefaced by OB. Oh, I wonder what cruel person could have assigned you as an assignment that was due Sunday night. Oh my goodness. Hexadecimal follows the same format as binary numbers in C, except instead of a B, you use an X for hex. So, 0x B9A243D0 is a hexadecimal number. So it's important to realize then, when we are printing a pointer, this bit here is not, that's not part of the number to be included. That's formatting for the number, not like digits of the number. Obviously, X is not a character in hexadecimal. It doesn't matter in hexadecimal, by the way, whether it's upper or lowercase. Decimal integers are, of course, you just write them. And octal digits are prefaced with a 0. So you have 0, then a number of octal digits. Remember that an octal digit, the maximum octal digit is 7. So, hexadecimal allows us to express numbers much more compactly than in binary, while maintaining a straightforward relationship to the underlying memory representation. So the difference between decimal and hexadecimal is that in decimal you have this weird relationship between the binary representation and the actual numeric representation. So, whereas, you know, an octal number, when you have 3 ones, that's the maximum digit, and if you have another one, you know, that the next 3 binary digits correspond to the next place value in octal, etc., etc. There's a nice, like, chunks of bits to place values relationship. The same way with hexadecimal, except in the case of hexadecimal, you're collecting 4 bits, not 3. However, a new decimal digit starts at binary encoding 1010, which is not precisely useful. You guys are going to find when you do embedded systems, you guys will have some embedded systems courses coming up in 3rd year. And when you do your embedded systems courses, talking to the Tron guys, Tron forever, woot woot, there's like a famous lab that they do with you guys. I did it on an FPGA. I don't know if it's going to be that or different. You know, I haven't looked at the curriculum since I took it 10 years ago. But, God, more than 10 years ago. Anyway, there's a lab where you have a 7-segment display, right? And the idea is that you take some internal counter on your microcontroller or your FPGA or what have you, and you print that number out, print it out, but what you're actually doing is you're just activating the segments of a 7-segment display such that each segment displays one of the decimal place values. The problem that you guys will run into is that in order to do that effectively, you guys have to parse out what the actual decimal digits are. If it were hexadecimal digits that you would be doing, it would be very, very easy, because all you have to do is byte mask them, right? All you have to do is take a byte mask of like the first 4 bits, then the next 4 bits, then the next 4 bits, and those are each individual numbers. But if you're dealing with decimal, like, it complicates things. And one solution to that problem is to space the decimal digits out a bit. Essentially convert a decimal number to hexadecimal, but just not use A, B, C, D, E, or F. And then you can use byte masking to capture your digits in a relatively straightforward manner. Anyway, I hope whichever prof is teaching that doesn't mind that I just gave away methodology for a lab that you guys will be doing next year. Anyway, so, proud and practical pointer passing. We are now going to talk about how to pass pointers as arguments to functions. All arguments are passed by value in C, unless the value that you pass is a memory address. So, passing a pointer is a way that C can simulate passing a value by reference. And we will refer to it as passing by reference, but you should still keep in mind that, like, in the underlying memory representation of what's going on here, you are actually passing a literal value around. It's just that that literal value happens to be a memory address. So, yeah, it's like, you know, C simulates pass by reference using pointers, but, you know, C simulates the ability to use decimal numbers. You know, like, it's a computer. Everything is a simulation. We can't, if we start considering things in computers that are simulated to be second-class citizens in computers, nothing would be a first-class citizen in a computer. So, anyway, passing by reference allows functions to modify the referred data in the calling function, which can be useful. So, consider the following code. We declare an integer foo. We declare a array bar. My function takes address of foo and bar. I will answer your question as soon as I am finished this slide. We use ampersand to pass the address of foo, but bar is already a memory address because, remember, arrays are pointers. In C, some array is defined as the address of the first element of some array. So if you don't have the index here, if you don't have the square braces, that means you can still work with the array. It's a pointer now. This is we're gonna see that this the square brace operator, and it's correct to think of it as an operator, is actually syntactic sugar for a little bit of pointer arithmetic and pointer dereferencing all in one step. So, yes, inside the function definition, foo will need to be dereferenced, but bar will not. So, in order to access the values of foo, you will have to explicitly put the dereferencing operator on it when you're using it in the function. With bar, however, you can use that in the ordinary way that you would use an array, because, as I said, the dereferencing operation is implicit in the fact that you are giving it square braces. So let me take a look at that question. Question: does the variable get stored anywhere at all? Like, does the computer actually know foo and bar? Yes. Yeah, those get stored in memory. So, do I have block vision for this? And this is, yeah, it might be a little more close. It might be a little more straightforward when we take a look at the next example. But in general terms, what's going on, we are declaring, let's imagine for a moment that this code is in main. Within main's stack space, because these are automatic variables, right? Because they're automatic by default. Within the stack space, a chunk of memory the size of an integer is allocated to the variable foo, and a chunk of memory the size of whatever the size of this integer array would be, that memory is also allocated and assigned to the variable bar, or the array bar. When we pass foo by reference into myfunc, what we are doing is we are using the address of operator to find the memory address of foo, taking that as a concrete value and passing it into the function. The thing about bar is that bar is already a memory address, so it already is a pointer to the first element of the memory that's been allocated. So we don't need to use the address of operator on it. We do, though, for foo. Hopefully that answers your question. Good question. So, here's an example. Let's cube by reference. So, function prototype, void cube by reference, takes an int n-pointer. An int star takes an integer pointer called n-pointer. In main, we declare a variable num and assign the value of 5 to it. We then print it to see what it is. We call cube by reference. We give the address of num, and then we print f to see it again. And we will. Do I have the output here? Yeah, it's in Blockovision. So I realize this is a lot of asterisks going on, but bear with me. So we take n star, we take the int pointer n pointer, we assign to the dereferenced n pointer. This is how you, by the way, this is how you assign something to the memory that a pointer is pointing to. Normally, you don't really think of operators as occurring to the left of the assignment operator. That's not normally a thing you think about. However, if you think about it slightly differently, it makes sense. If you think about this side of the assignment operator as having to refer to some memory, right? It has to be a variable. It has to be a chunk of memory that you're assigning into, and this as the value that you're assigning into that chunk of memory. That makes sense. If we left out the asterisk, we would be assigning to the pointer itself, and if you were to assign a integer value into a pointer, you would be pointing to the memory address like 125 if 5 was the input, which generally speaking is undesirable. So we dereference the pointer in order to perform assignment on the memory that the pointer is pointing to. And the value that we are assigning is the pointer dereferenced multiplied by itself 3 times. So, for those of you who are wondering, what alternative do I have to using the power function to compute a exponentiation? Always remember that exponentiation, when it comes down to brass tacks, is repeated multiplication. So, by dereferencing the pointer, we get the value of 5 out of each of these. So 5 times 5 times 5, assuming the input is 5. And then we assign it there. So let's see what this looks like in Blockovision. So, main calls cube by reference. First of all, it assigns number to 5. Then cube by reference at ampersand number. We then, when we invoke cube by reference, during the regular definition of cube by reference, we have n-pointer as memory that belongs to that function. However, it's undefined because nothing has been passed into the function yet. After cube by reference receives the call and before n-pointer is cubed, we have we have nPointer assigned the memory address of number. Now, number is still inside of main's call stack frame, right? Number has not left the memory region dedicated to the main function. It's still in there. However, because nPointer is a reference to it, we can actually modify it. So, after nPointer is cubed and before the program returns to main. So, this operation, first of all, these pointers are dereferenced, the values extracted, so 5 times 5 times 5, that's computed, that becomes 125. The value 125 is assigned to the dereferenced pointer, so number becomes 125. So there you go. I have a question. Bloop. So is this example comparable to dealing with global variables in Python? No, it's a slight So it's like related but distinct. So in order to draw the distinction between what we're doing here and a global variable, we need to revisit the concept of what global means in the context of a C file. Actually, let me just bring up the slides where we talked about that stuff, because that's here we go. So in C, remember, we have automatic variables, external variables, static variables, and registers. So remember that external variables are in C what you would think of as global variables in Python. They are common to all of the functions in the program and can even be read across multiple files. In contrast to that, automatic variables are analogous to local variables in Python. So what you are doing is you are not considering you're not considering the automatic variable in main to be a global variable. It is still a automatic variable. It is still stored in the stack. It is still initially garbage. It is still its lifespan is still only within the main block, right? And you can generalize this. If this were some function other than main, an external variable would be visible in main, the function that called cube by reference, and cube by reference. So this passing by reference does not interfere with the the properties of the automatic variable in the main function. It's still limited to the main function. It's still local to the main function. It's more like let me see if I can come up with an analogy. Okay, I've got an analogy. It's not a perfect one, but here we go. So let's imagine that your program is a table, right? Let's imagine that a plate is the stack frame of a function. So there's a main plate, there's a there's a cube by reference plate. There are plates on the table. There's a jar of olives on the table. That jar of olives is global variables. Both of the functions can pick global variables. They can both eat the olives that are in the center of the table. Now let's imagine that both of these plates for main and cube by reference also have olives on them, right? It's not that cube by reference is picking from the jar of olives. cube by reference is going in onto main's plate and picking up one of his olives and like stuffing it with almond instead of pimento and then putting it back. Or maybe cube by reference is inserting the almond directly and replacing the pimento, overwriting the pimento without, like, it's got like a magic arm that just kind of does it on main's plate. Anyway, that's as good as I could do for an analogy. I hope that's okay. We are learning computer science with olives. Anyway, so in order to accept a memory address as an argument, that fact must be specified in the argument's type information. So if you'll notice, we are specifying that this is a pointer using the star. Once again, same rules as pointer declaration. That's not a pointer, excuse me, but it is a declaration. I'll answer your question once I get to the end of this slide. In this example, we replace the following operations with, I'll run through the operations that we would used to have to compute this, and we are replacing it with the following. So the thing we were doing before is that we would pass num by value to cube by reference. We would then compute the cube and return it to main, and then we would assign the return value of cube by reference to num. Notice in this example, cube by reference does not contain a return expression, and yet it is still able to return information. So we're sort of this is a very simple example. You can obviously use this type of technology for more interesting things than just not having to use a return statement, right? But, you know, it makes a good example. So we've replaced that operation with the following. We pass the address of num to cube by reference. Cube by reference computes the cube and stores it in that memory address directly. Stylistically, pass by value is preferred unless the situation explicitly calls for pass by reference. Passing by reference in this way violates the principles of least privilege. So this is kind of another one of these possible but not recommended kind of situations. Generally speaking, you don't want to pass by reference in this manner unless the specific situation calls for it. The specific situation may call for it, particularly in situations where we're dealing with more complicated data structures, or when we're, you know, modifying an array. If an array is sufficiently large, copying it value per value as an argument into the function is impractical, and passing it back out again, you know, value for value is also, like, that's a lot of copying, and you don't necessarily want to do all that copying. But, you know, you should always try to adhere to the principle of least privilege. Back to our olives on plates analogy, generally speaking, I hope that analogy was somewhat humorous, because the idea of cube by reference, you know, picking up an olive and messing with main's olive should be like, oh, that's rude. That's not a thing that I would do at a dinner party. So yeah, if it's not a thing that you would do at a dinner party, you should also not do it in C, to the extent that that's possible. Unless it's like the mom function who's cutting up the steak for baby function or something. Okay, let me see what this says. When cubed by reference is done, num is equal to 5 or num is equal to 125. Num is equal to 125 when cubed by reference is finished. Do I have the code here for it? Passref, is that it? Let's see. Yeah, there we go. Alright, let's run passref, and you can see it actually run, which is always useful. GCC wall. What did I call it? Bloop, bloop, bloop. Passref. .c. Output. Passref. Here we go. Oh, we've got an error. Did I make a silly error? Oh, yes. Okay. So we're going to talk about const at some point during this lecture. Basically, the const keyword makes an argument read-only. Sometimes I mess around with these files while I'm working out the slides. So, passref. There we go. First num is equal to 5, then num is equal to 125. I'm not fibbing. I am not joshing you. I'm not pulling your leg. This is how computers work. Yeah, so pass by reference, it's not quite so strong a don't do this ever for any reason as go-tos. Incidentally, some of the TAs have told me that some people, in their infinite wisdom, decided to use go-to statements for the purposes of the assignments that they submitted, and I'd like to say to you people who think that go-tos are an appropriate way to conduct yourself, it is extremely rude and extremely unfashionable, and I do not want to see a single go-to statement come back in any assignment that you guys submit from this point forward and for the rest of your lives, unless we're doing assembly programming. Thank you very much. So, arrays are pointers. Not to belabor the point too much. The syntax for passing an array as an argument to a function is the same as passing a variable by reference. This is because the compiler does not differentiate between pointers and one-dimensional arrays. One-dimensional arrays are pointers. Like so many things in C, that means it's your job! Yay! You're the one who has to differentiate. It's up to you to write your functions so that they are using their arguments as intended. This means that documentation is critical. It is absolutely important that either your variable and argument names and function names are descriptive, or you comment your code such that it's clear what your arguments are supposed to be, preferably both. An array is actually a pointer to its own first element, as we said. We can perform arithmetic to traverse arrays without the indexing operator, and when we get into arithmetic, we'll be talking about that. Yes. Well, it is dramatic. I can't believe that I wrote on the slide, "This is forbidden knowledge, never use it," and then people used it anyway. It's amazing to me. Like, did they just want to see if they could get away with it? Like, it boggles my mind. So, const and the art of mental stillness. Problem. Whenever we work with pointers, there is a possibility of pointer misuse resulting in a segfault. Boo, segfaults. We can prevent arguments from being modified by using the const qualifier. And by the way, this doesn't only work on pointers. This works on, any argument. Any argument that there's no reason why the function should need to modify it. You should put the const qualifier on it. That makes it read-only, which prevents the function from, messing itself up in certain ways. A good example of this, you guys have noticed, I hope, on the assignment so far, that when you pass an array to, like, a sorting function, for instance, you are actually required to also pass the length of that function or the length of that array into the function. This is because when, for whatever reason, I'm not quite sure why actually, it's like a practical thing you have to do. When you pass an array into a function, it loses its sizing information. So it's impossible to reconstitute what the length of the array is inside of a function. That's only possible inside of the context in which that array was generated. Otherwise, that's manual bookkeeping that you, the programmer, have to do. However, the size of an array that you're sorting is not something that's going to change as you progress through the sorting algorithm. So, a good thing to do would be to make that into a const, because it is something that should be read but not written to. So, if you try to modify a const argument, it will result in the following compiler error in GCC. That was actually what this compiler error. Previously, I had a const keyword const tag right there, which meant that this operation here was invalid syntactically. So, that's what caused that error. Boop. Using const to restrict functions from modifying things that they shouldn't modify is good software design. In general, a program should have only enough data access to accomplish its task, and not one smidgen more. That's the principle of least privilege, expressed succinctly right there. A program should not have more access than it needs to accomplish its task. So, let's talk about pointer arithmetic. And this is a quick little, poorly drawn comic, but, yeah, it's still funny. Hey, C, could you zero out the data at these addresses? Sure thing. Poof. Wait, what data did those addresses point to? Looked like some kind of critical OS data kernel or some such. What? Meh. This perfectly encapsulates C's attitude. This comic, I have not found one yet that more perfectly encapsulates the attitude that C has towards you, the programmer. It is perfect. Boop. No clever quote this time, but I did learn that the internet seems to think indirect means passive-aggressive. It's like, try looking for a comic based on indirect reference. It's impossible. Question. Facebook has entered the chat. Oh no! Not Facebook! Evil itself has become incarnated. So, in this particular case, we're going to go right into a code example. So, we include stdio.h. In our main function, we have foo, the array, which is 0, 1, 2, 3, 4, and we have a short int bar, which is, that seems like that's an error. These are floating point literals being assigned to a short int. Pay no attention to the little man behind the curtain. For int, okay. So what this guy is doing is it's going through each element in both of these arrays and printing what the pointer is for each index. So this is interesting. For foo, looking aside from that business where I'm accidentally assigning float literals to integers, what you get is the pointer at address 0 is blah 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 190. At address 1, it's 194, then 198, 19C, and 1A0. So notice that each one of these addresses, first of all, they occur in a regular pattern. Second of all, each one is incremented by 4 from the last one. With bar, we are going up by 2 each time. So the increment that these are increasing by is actually the size in bytes of the underlying data type. So if you look, foo is an integer. Integers are 4 bytes in C. A short integer is half that size. So a short int is 2 bytes. So that's why this one goes up by 4 and this one goes up by 2. But this is also a literal demonstration that when you are allocating an array in C, that is continuous memory. So the correct way to think about it is that foo0 occupies addresses 190, 191, 192, and 193. And foo1 occupies 194, 5, 6, and 7, etc., etc. In Blockovision, this is, not quite the same names and values and such, but, there it goes. Notice that the location is the beginning of that number in memory, right? So v0 will occupy from whatever the value of the pointer is until you have reached the size of the thing. So there you go. Let's talk about our old friend plus plus. If we notice in the previous slide how foo's memory addresses are 4 bytes apart, and, not if we notice. Notice in the previous slide how foo's memory addresses are 4 bytes apart and bars are 2 bytes apart. The array is continuous memory, and each element is allocated the size of the base data type of the array. You'll hear me refer to that as bit width as well. Bit width. If we wish to perform a pointer arithmetic to traverse the array, we need to know how big the steps are. Well, technically, the compiler knows how big the steps are. It's actually surprisingly easy for us, but it's important for us to sort of understand it. Operators can mean different things when applied to arguments of different types. For example, there's a difference between floating point and integer division. Plus plus, when applied to a pointer, will automatically take the size of the data that it's operating on into account. So plus plus will increment a pointer. It will increment the pointer to the next valid memory cell. So if we had foo1, if we had this memory address, this one right here, and we performed the plus plus operator, and this was stored in a pointer data type, we would get this one. However, the typing information would need to be known. So here is an example of traversing an array with pointer arithmetic. So we have our main function. We have a character array that says dated reference. We declare a character pointer, a foo pointer, and we assign it to foo. We then have a while loop, which is slightly dangerous, because if the null character did not at any point appear, this would be an infinite loop, or the thing would probably crash out on a seg fault. Yeah, it wouldn't be an infinite loop, it would crash out on a seg fault. We are printing each character in order in parentheses, and then terminating with a new line character. But if you notice here, we're dereferencing foo pointer, and then we are also incrementing. So when we dereference the pointer and it's pointing to a particular cell in an array, we get the value from that cell in the array. In that way, our output for this program is dated reference with each character inside of parentheses, including the space. What happens when you increment a pointer that is not an array? Does it just go to the next bit? Well, it skips a number of bytes equal to the bit width of the memory type that the pointer is associated with. So if it's a short int pointer, it would skip 2 bytes and then give you that, whatever is at that place in memory. And if it was a long int, it would skip 8 bytes and give you whatever is... It would skip 8 bytes and then give you the value at the next 8 bytes. But yeah, it would just move the pointer around in memory by a factor of however wide the data type is that you're operating on. So yes. Once again, possible but not recommended. The problem with doing that to a variable type that's not an array is that you're essentially, you don't know what you're reading. It could be memory that has been allocated to another variable. It could be memory that has not been allocated to anything but is still within the memory space of the function in the call stack. If you do that often enough, you could exceed the bounds of the memory space that's been allocated to the function that you're currently processing. That would constitute a stack smash type error, which Linux is pretty good at detecting. So, yeah, so there we go. So this particular, so this only works because strings are null terminated, of course, but that's some array traversal. Let's see, okay, we can do this slide at least. The following are valid operators on pointers. We got plus plus, minus minus, plus minus, plus equals, and minus equals. In each of these cases, the number you are adding / subtracting to / from the pointer is implicitly multiplied by the bit width of the data type. For example, if ptr points to an int, then pointer plus 4 would move the pointer by 16 bytes, since the bit width of int is 4 bytes. Pointers may also be subtracted from one another, but only meaningfully if they point to the same array. So pointer A minus pointer B yields the number of array elements difference between the two pointers, not the number of bytes difference. So that's an important thing to know too. So you can tell that if you're using pointers instead of like an index variable to traverse your array, and you've got 2 of them going on at once, you can tell the difference between them by performing subtraction. But, you know, subtraction between pointers that are not in the same array is not meaningful, because the only thing that will tell you is their relative positions within memory. It's not meaningful information unless you're specifically interested in their positions in memory, and whether one is, like, higher up than the other or whatever. And you could, you know, you could just as easily cast the pointers as integers and use a comparison operator on them. It would do just the same. It would do the exact same work. And, like, it's not really useful because it very largely it doesn't matter at all where something is in memory, so long as it is in memory, right? But, yeah, anyway, I think that will be our last lecture before the break. So, huzzah! Good show, good job, everyone. I'm very pleased to say we're here and not over there. Very, very good. If anybody has any questions for the professor before we have our break for the week, please enter them into the chat now. Otherwise, I will log off and go get some lunch. There will not be an assignment due next weekend. There will be an assignment due the weekend after that. So we are on a 2-week model for assignments now. I'm hoping that I can pull together enough resources to be able to get the assignment 3 out to you guys by the end of the weekend. But that's, yeah. I love how memes are a thing. Cool. All right. Thank you very much, folks. Incidentally, if there's anybody is anybody still listening to this? Okay, there's people still listening to this. So, on Thursday of next week, I'm going to be having my wisdom teeth removed. So, if you guys want to, if you guys are going to be, don't email me Thursday or Friday of next week, because I'm having my wisdom teeth yanked, and I'm going to be hopped up on all of the whatever it is they hop you up on, so that they can knock you out, so they can rip 4 of your teeth out. So just Thursday, Friday, I'm going to be AFK all day, so there we go. I hope the swelling goes down before my lecture on Monday. That's all I can hope. It might be super amusing. My lecture next Monday might be super amusing, because I might have a puffy face still from having my wisdom teeth ripped out. You know those things actually poke up into your sinuses? It's crazy. Anyway, take her easy, folks. Have a good break. I know I won't get much of one, but hopefully you will. See you in the next one.